How accurately can we predict the number of primes below 1 million or any number? Surprisingly, the answer depends on the Riemann hypothesis. If the hypothesis is true, our prediction is only off by about the kind of error we see in a coin toss. Pretty accurate. All of this conclusion begins with j of x, Riemann's prime counting function. Unlike the smooth Li of x, Gauss suggested, j of x captures even the finest isolations. Here, the key part is the second term. It adds up the contributions of complex numbers, called non-trivial zeros. It brings Li of x closer to the jagged pi of x, the actual number of primes. The Riemann hypothesis came from this term. Let's express the effect of the non-trivial zeros using a formula. A0 row equals beta plus I gamma. The contribution produced by a single zero is roughly on the scale of x to the beta divided by log of x, simply on the scale of x to the beta, because x to the beta is what mainly controls the size of the term, and the combined effect of all the zeros is on the scale of x to the beta multiplied by log of x, simply on the scale of x to the beta as well. It is the same as the contribution by a single zero. That's because the contributions produced by the zeros partly cancel each other out. For the details, please refer to the previous video. Now we are ready to move to the Riemann hypothesis. It says the real parts of all non-trivial zeros are exactly 1/2. That is, beta equals 1/2. So the combined effect of all the zeros is on the scale of x to the 1/2. It stays close to the root x scale. Here's the thing. This scale eventually explains the difference between pi of x and Li of x. The error between the actual number of primes and the estimate given by Li of x. Let's see why. We can rewrite pi of x minus Li of x like this. The first part comes directly from Riemann's explicit formula. Since these two terms become negligibly small, this part is almost the same as the combined effect of the zeros. Look at the second part. J of x was originally defined as a function that counts primes and powers of primes with weights. So j of x can be written this way. If we rearrange this, we get this. So this is pi of x minus Li of x. Among these terms, this is the largest one. This term is still no larger than the square root scale. Since the remaining terms are even smaller, we can ignore them. So the main structure of pi of x minus Li of x comes from the effect created by all the zeros. Therefore, if the Riemann hypothesis is true, pi of x minus Li of x stays close to the square root scale. Interestingly, this is exactly where prime numbers connect to coin flipping, because in coin flipping, the size of randomness also appears around the square root scale. If you flip a coin 100 times, you expect about 50 heads, but you almost never get exactly 50. There's always some deviation. The typical size of the deviation is on the square root scale, roughly root 100. So most of the time, the number of heads falls somewhere between 40 and 60. You might think this is not very accurate. After all, the margin of error is about 10%. But once you increase the number of flips, the picture changes completely. As the number of flips increases, the absolute deviation grows too. But even though the deviation root x gets larger, the relative error root x over x gets smaller and smaller. That's because the denominator x grows much faster. So the prediction becomes more and more accurate. Now bring this back to primes. If the Riemann hypothesis is true, pi of x minus Li of x stays close to the square root scale. That is, as x grows larger, the relative error gets smaller. The actual counter primes and Li of x become nearly identical. Li of x converges to pi of x. This also agrees with the conclusion of the prime number theorem. That's why many mathematicians believe the Riemann hypothesis is true. Primes appear irregularly, but the number of primes predicted by Li of x does not go too far from the actual number of primes. The error does not disappear, but it is controlled. Primes are not completely random. They are deeply structured. There is a hidden order in the way primes are distributed. That's the conclusion if the Riemann hypothesis is true. But if the hypothesis is false, then at least one non-trivial zero has a real part greater than 1/2. Beta is greater than 1/2. The larger beta becomes, the larger the wave created by the zero becomes. As a result, the overall effect produced by the zeros becomes larger than the root x scale. This means the error in pi of x minus Li of x can become much larger. There may be cases where the prediction made by Li of x is far from the actual number of primes. In that sense, primes would appear to behave far more irregularly and randomly. The convergence of Li of x toward pi of x would also become slower. So far, an enormous number of non-trivial zeros have been checked by computers. All of them lie on the line where the real part is 1/2. But we cannot guarantee that the next zero will always lie on the same line. So one question remains: is it actually true? If so, who will be the first one to prove it?